So in this video, we're going to talk about angular momentum, which is the very last topic in the angular series that we have. And if you remember, whenever we talk about anything angular, there is always a pair that goes with it, linear, something that we've studied already. So when we talk about momentum, if you remember, the equation for momentum is mass times velocity. So when we talk about angular, our angular momentum, the symbol for that is an L. So this is going to be our angular momentum. When we look at the mass, if you remember, that is inertia, and that's going to be in angular our moment of inertia, or I. And then when we look at linear velocity, the equivalent or the pair to that of our angular will be our angular velocity, which is omega. So this will be angular velocity. Now, another way that we can look at it, if you remember talking about momentum, we also had an equation that was the impulse, J, is equal to the change in momentum. And if you look at that impulse, it is force times time is equal to change in momentum. So for an angular equivalent to that, we could say our angular force is going to be the torque. Time is still time, whether you're looking at linear or angular, whether you're looking at 1 dimension or 2 dimensions, it's time, or 3 dimensions or 4. And then our change in angular is going to be the change in L, since we talked about this being angular. What this equation shows us is that as long as the torque is constant, or as long as there is no torque, then angular momentum is conserved. Then angular momentum is conserved. So if we don't have any torque acting on an object, then the angular momentum has to be conserved. And one of the best examples that we can give for this is going to be a figure skater spinning. Figure skater spinning. So if I take my figure skater, and maybe they're here like this, leg up, arms out in the air, spinning around this way, so doing sort of a spin like that. And then what they do is they pull their arms in, they pull their legs in, so they crisscross on the legs, they bring their arms up like this. If you remember watching any of these, then they spin so much faster because they're pulling their arms and their legs inward like that. So let's just, for the heck of it, put some numbers to this and say that this moment of inertia of the skater with their arms out like that is going to be 6 kg/meters squared, and that the omega of them, or the angular velocity, is going to be 2 radians per second. Then once they pull their arms in, we can say that their new moment of inertia, because it's dependent on the radius, remember the closer you get to the radius, the lower that moment of inertia is going to become. So we'll have 4.5 kg/meters squared, and we want to find out what is their new angular velocity going to be. So because there's no torque acting on the two of those, we can say that the angular momentum in has to equal the angular momentum out. So I omega has to equal I omega, and then I can say 6 times 2 is equal to 4.5 times omega. And when I solve for my new velocity, I found that the velocity has gone up to 2.66, repeating, radians per second. So that's one example that we can use with the conservation of angular momentum. In the next example, we're going to talk more about using this equation and how to go a step further with it.